Yeah, this quiz had some teeth, especially the last question. Let's see. Oh, good old Anne. Number one says this: a conducting wire is carrying a current towards the top of the page as shown below. Due to the presence of a magnetic field, the wire is experiencing a force directed out of the page. So F is directed out of the page. What's the direction of the magnetic field? So this is our high five hitchhiker right hand rule. As far, no, 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 yes, 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 Anderson. No, 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 yes, yes, yes. As far as I'm concerned, I can give you any two of the directions and you can find the third. So in this one, they're telling me magnetic field is, sorry, current is up the page. And it's telling me it's getting a force out of the page. If I use my whiteboard as my reference, I got to do this right. Yeah, my palm would push out of the page. What direction are my fingers pointing? What direction is the magnetic field? Left, left. Yeah. And then number two, same idea, but now it's experiencing a force to the left. So I would have current pointing up. My palm pushes to the left. Now my fingers are the magnetic field, and we are into the page for number two, into the page. Part of the tricky part here is I can't come up with a stupid acronym because the word force and the word field both start with letter F. So what I've done, thumb is the current, fingers is the field. You can use F, and then palm pushes, P and P. Palm pushes a force. It's the best I got. Number three, a stream of protons. Okay, they've given me a magnetic field. I'm going to use QVB, and I guess they want me to get the V by itself. That's going to be the magnetic force. By the way, I use FB for magnetic force because I want to reinforce that the letter B is the abbrev for magnetic field. You may see some textbooks use, and I think a couple of the questions in the homework, they use FM for magnetic force, which is okay. I just want to reinforce that B is my abbrev for magnetic field. So it's going to be, anyways, the force divided by QB. What's the force? 5.8 times 10 to the negative 14. Q, it's a proton, 1.6 times 10 to the negative 19. Don't use 1.67 times 10 to the negative 27. Look at the units. That's kilograms. It's not a mass. I'll make fun of you. Q is charge. And then the magnetic field is 0.6. Speed is, I have no idea. 5.8 times 10 to the negative 14 divided by bracket 1.6 times 10 to the negative 19 times 0.6. I get 6.04 times 10 to the fifth meters. Is that right? Per second. Is that correct? So if you got that 2 out of 2, otherwise I would probably give you a half mark if I saw the QVB, a half mark for getting the V by itself, a half mark for the numbers, and a half mark for the answer. First thing I did, Dueck, really? 0.08 meters. Dueck, really? 0.042 meters. They want the force. Oh, no, they want the magnetic field. They gave me the force on the wire. So the force on a wire is Bill. They want me to get the B by itself. That's going to be F divided by IL. The force is pretty easy. It's 0.024. It's 2.4 times 10 to the negative 2, but it's less work to type that in, so I unscientific notationed it. The current is 5.2 amps. The real question is, which L am I going to use? Am I going to use the 0.08 or the 0.042? I'm going to use the stuff that's in the magnetic field that's feeling the force. Which length of wire is feeling the force because it's in the magnetic field? 0.042 meters. So I'm going to get 0.024 divided by bracket 5.2 times 0.042. Did you all get I guess if I round that off, it's going to be 0.11 Teslas, 0.110. But if you got that, 2 out of 2. Otherwise, same as before, I'd probably go half mark, half mark, half mark, half mark. These last two questions would probably make good multiple choicey questions, because as I've said, in F equals Bill, I can give you any three, find the fourth, and in F equals QVB, I can give you any three, find the fourth. What's the direction of the magnetic force? Okay, magnetic field, sorry, current is to the left, and magnetic field is into the page. Oh, that's convenient. My hand pointed that way anyways. Down the page, is that correct? Before you turn the page, what kind of using principles of physics-y questions could I ask? Oh, I could say, suppose we double the current and double the magnetic field. What happens? Suppose we double the current and cut the magnetic field in half. What happens? I could give you some mix and match, and you can always crunch the numbers, or you can do it algebraically. An electron, it's an electron. Traveling, moves perpendicular. What's the magnitude of the force? So an electron moving through a magnetic field, that's QVB. And you know what? This is going to be straight plug and chug. I have the F by itself already. Q, it's an electron, 1.6 times 10 to the negative 19. V, 6.2 times 10 to the 6th. B, 0.0085 or 8.5 times 10 to the negative 3. I wrote it that way because it's less typing. 1.6 times 10 to the negative 19 times 6.2 times 10 to the 6th times 0.0085. Did you all get 8.43 to 8.43 times 10 to the negative 15? People are nodding. Is that what I said? Yeah. Is that a big force? Yeah, for the electron, it's massive. You can figure out the acceleration by dividing by the mass of an electron, and you'll realize, holy smokes, for the electron, that's a massive force. B, this is forced into a circle. Okay. You could probably use your answer from A to do B. I did the full derivation, Anderson. I said magnetic force is what's pushing me in a circle. I said QVB equals mv squared over r. Hey, Anderson, one of the v's cancels. Get the r by itself. Where is it right now? On the bottom? Yeah. Times it to the top and divide the QB over. Jazz and Deep, I get R equals MV over QB. By the way, from last year, what is mass times velocity? We did a whole unit on it. Anybody remember what mass times velocity was last year? Momentum. This also involves conservation of momentum. This is why particle accelerators and smashing particles together gives us such nice results, because momentum is conserved and energy is conserved. What we do is we smash stuff together really fast. We add up all of the observed energies. Stuff's missing, you know what you're looking for. We add up all of the observed momentums. Stuff's missing, we know what to go look for, because the momentum does have to be conserved and the energy does have to be conserved. So this is how we can predict energy levels and masses and velocities of missing particles that we didn't detect, but we know had to have been there, because when we added everything up, we came up short. Just saying. In this equation, again, if I give you any 4, you can find the 5th. This would also make a nice using principles of physics question. I might say, okay, what if instead of an electron, what if it's a proton at the same velocity? Does the radius get bigger or smaller? Or what if I increase the magnetic field? Or what if I increase the speed or decrease the speed? What happens to the radius? Or what if I could ask you all sorts of mix and match questions. This is straight now plug and chug, though. It's going to be the mass. It's an electron. 9.11 times 10 to the negative 31. It's going to be the speed. What did they say the speed was? 6.2 times 10 to the 6 all over Q. It's an electron, 1.6 times 10 to the negative 19. And B was 0.0085. Here I get an answer I'm kind of meh on. I like my answers to be reasonable. 9.11 times 10 to the negative 31 times 6.2 times 10 to the 6th divided by 1.6 times 10 to the negative 19 times 0.0085. Look for typos. I think that's good. Yeah, did you get 4.15 times 10 to the negative 3? It's 4 millimeters, which is a pretty tiny radius. I have this electron bending too fast. I need to probably bump down the magnetic field or increase the velocity, something to make the radius a little larger. But oh well. 4.15 times 10 to the negative 3 meters. Was that correct, Mr. Dueck? Yeah. What's the kinetic energy of the electron? I stuck this on just to do some basic review because they gave you everything you need. It's going to be a half mv squared. It's going to be 0.5. It's an electron, 9.11 times 10 to the negative 31. V was 6.2 times 10 to the something. 6, don't forget the squared. Don't forget the squared, Mr. Dueck. Almost did. Did you get, is it 1.75 times 10 to the negative 17? I made a typo. No. Am I right? Is that right? 1.75 times 10 to the negative 17? Units, energy, joules. Okay. Oh, I forgot to do part marks for this previous one. I would probably go a half mark if I saw that, half mark if I saw that, half mark if I saw that, and a half mark for the answer. Here, I guess 1 mark if I saw that, half mark for that, and a half mark for the answer. What's the magnetic field strength in a solenoid? So the magnetic field strength for a solenoid is mu naught N times I over L. Or the other version is if they give me the number of turns per meter. Here, they want the magnetic field strength. Again, I would have no problem because there's 1, 2, 3, 4 variables. Giving you any 3, get the 4th by itself. Excuse me. It's going to be 4 pi times 10 to the negative 7, the permeability of free space. N is 600. A is 4.5. And nice try, Dueck, 0.032 meters, not 3.2. 4 pi times 10 to the negative 7 times 600 times 4.2 divided by 0.032. 4.5. Why did I write 4.2? I don't know. Let's fix that. I even wrote it wrong. Give me a second here. Did you get 0.106 Teslas or no? That's you nodding? Teslas. I guess here I would give you 1 whole mark for recognizing the equation, half mark for the numbers, half mark for the answer. I've had a few kids ask me about this. I'm really asking in this question, do you understand how we define magnetic field lines direction? How do we figure out the direction? Magnetic field lines point from what to what? That means if they're pointing that way, there must have been a North Pole here, there must have been a South Pole here. And now, unlike poles attract, this North Pole will rotate until it's as close as it can get to that South Pole. This South Pole will rotate until it's as close as it can get to that North Pole. And yeah, you're going to end up in orientation A. That's what a compass does, right? A compass is just a magnet, and the North Pole of the magnet points that way, which we've chosen to call geographic north, but in the Earth, there's a magnetic South Pole down there. I like number 8. This solenoid is carrying 5 amps of current, so it's basically having a uniform magnetic field inside there. Now, that magnetic field is exerting a force on this tiny chunk of wire right there. Why isn't it exerting a force on these 2 longer chunks? Because they're parallel to the field. It wants me to figure out how many turns of wire are in the solenoid. So I started out pretty basic. I said, okay, B equals mu naught N times I over L. Jesse, what do they want me to get by itself? Okay. I said, this is not too hard. N is going to be B times L divided by mu naught times I. And then I went, ooh. Well, first of all, which L? This is the solenoid, this length, because it's the solenoid. Which A? This is the solenoid, this A, because it's the solenoid. But I don't know B, the magnetic field strength. So I paused and I said, okay, I need B. Well, I said they also gave me a force, and I know that the magnetic force on a wire is Bill, so maybe I can get that B by itself, because that's going to be the same magnetic field strength. Maybe I can go F over IL. Now, the force was easy enough. Newtons, 0.048. Current, it's the force on this small wire, so it's going to be the current in this small wire, 8 amps. Length, it's going to be the length of this small wire, which is 0.025. I'm going to get a magnetic field strength. This might work out nice. 0.048 divided by bracket. Is it 0.24? 0.24, yeah. Teslas. Walk it over to here. I end up with N equaling 0.24. What was the length of the solenoid in meters? 0.16. Mu naught, 4 pi times 10 to the negative 7. What was I in the solenoid? You can see how this would lend itself, first of all, nicely to a nasty multiple choice, because one of the answers would be if you used 8 amps right here. One of the answers would be if you used 0.025 right here. One of the answers would be if you used 5 amps in this equation, or 0.24 meters in this, or sorry, 0.16 meters in this equation. So lots of mixes and matches. I have no idea what the, is it 6,111 or something, or 112? I did that from memory. I didn't actually solve it. I'm just going to go to 3 sig figs. I'm going to say 6,110, and the correct unit for turns, strangely enough, is turns. If you got that, I would give you 7 out of 7. Otherwise, I would probably give you 1 mark for that, 1 mark for that, 1 mark for 1 mark for that, 1 mark for that, 1 mark for the answer, that's 5. 1 mark for the numbers, that's 6. 1 mark for the answer, that's 7. Can you give yourself a score out of 7, please? Any questions or lawyering with me? Now is the time.